Okay, let's get started. Good afternoon, everyone. Welcome to the HAO Colloquium. And today we are very glad to have Professor Lunjin Chen from University of Texas, Dallas, to give a talk. Here's a brief introduction of Professor Chen. He is a Eugene McDermott Professor of Physics at the University of Texas at Dallas and specializing in space plasma physics and magnetospheric physics. He got his PhD degree from UCLA in 2011. And after 2-year postdoc there, he joined as an assistant professor in 2013 at UTD. And he has extensive experience, more than 160 publications. Well, it's a big number. In the topics of magnetosphere physics, plasma instability, plasma wave propagation physics, and wave particle interactions. And today he's going to talk about modeling electron microbursts due to curls. So please take it away, Lunjin.
Yeah, thank you, Don, for the nice introduction. So the topic I'm going to dealing with today is the electron microbursts and then the cross wave. So I think I'm obligated to explain what are the two phenomena. So first of all, the cross wave, as you know, the cross wave are Whistler wave, electromagnetic radiation frequently observed in the magnetosphere. And if you look at the fine structure, the high resolution dynamic spectrum for the electromagnetic radiation in the magnetosphere, you often see those type of thing like this is below the electron joule frequency, this half electron joule frequency. So in this below the half electron joule frequency, you see those Whistler wave, but they are not like a broadband emission. They come with a narrowband emission with rising frequency. So we call those rising tone elements structures and we call this as cross waves. And then of course sometimes they have down turning frequency. Those are falling tones. And very often above the half electron joule frequency, you see broadband emissions. We call this the emission above the half electron joule frequency as upper band, and this below the electron joule frequency will have a lower band. So the topic by the cross wave in this talk, I mostly refer to those lower band rising tone elements. So we call those elements. And then as you can see, those elements has a short time duration. It's about a fraction of a second. And the frequency can rise from the 0.1 all the way to 0.5 electron joule frequency. So those are, and then those are typical features of the cross wave. And then you can see the cross element does not come alone as one. They always come as a group. So you see there's a bunch of cross wave element here and another group here. And on the other hand, the electron microburst. Electron microburst can be seen by the particle detector orbiting in the NEO orbit. So here's the example of the particle detector from SEMPEX measuring the electron flux, integrated electron flux about 1 MeV. And this about the 6 minutes. This is like a 6 second also. This is 60 minutes duration. And you can see this very nice, and the red line represents the measurement of the electron flux. And you can see there's a nice background electron flux and this from the SEMPEX observation. And then on top of that, you see those spiky structures. And those spiky structures are known as electron microbursts. And those are the relativistic electron microbursts. And they are very short-lived, only in like a few tenths of seconds, but very intense electron flux, like at least about 1 order of magnitude greater than the background. And then they can also, and then this relativistic electron microburst can also be seen from the lower altitude through the balloon measurement by counting the X-ray photons. And the other thing I want to mention here is, although this shows just a relativistic electron microburst, but the recent study also showed that the electron microburst can have energy down to the 30 kV ranges. So it's a very broad range of the electron precipitation. And then further looking at the statistics of this electron microburst. So this is also the typical duration, average duration, and then the of the electron microburst, and also the spatial distribution of electron microburst. So the blend, so this is no nice side on the bottom, and then this on the top, and then you can see the currents are fairly confined from the pre-midnight to the noon sector and the morning side here. And the blank here is so the statistic is not good, so meaning very few events. And then if you look at the duration, so not only the and then the L range is from the 3 to 6, and not only the 3 to 4 here, 3 to 5, sorry. And then not only they are very organized in terms of local time. If you look at the microburst duration values, they tend to have a pattern. So you still have a lower values on the midnight, and then the higher values by a factor 2 increases when you move to the daytime. So there's a very systematic variation of the microburst duration as well. So keep that in mind, and then I will adjust this problem later on. So that's the relativity electron microbursts. And then, as I mentioned, the electron microburst covers a wide range of the energy. So I already show you example of the above MeV electron flux from the SEMPAX observation. So SEMPAX also carries a particle detector at low energy, like greater than 400 keV, greater than 25 keV. So if you look at it, then at the same time, over this 15 minutes, also you can clearly see the enhancement occur throughout all those energy ranges. And then, in addition to that, if you look at this MeV electron flux, you can see this enhancement is not a single electron microburst, and there are actually a group of microbursts. So we call those individual spikes as the electron microbursts. So they count as a train, as a series, and then the train of microbursts can last for several seconds. And then sorry, this is second, and this is 15-second measurement. And then the individual microbursts can only last like less than a second. And on the left-hand side is a measurement from the May satellite at the 6,600 kilometer altitude. So they measure two things, and the plot shows two things here. One is the electrostatic analyzer electron flux at this 6 keV. So you can see those enhancement here, enhancement here, enhancement here. And on the bottom side, actually you saw the photon intensity for this at this 670 nanometer wavelength. So it's basically the measuring the pulsating aurora. So you can see there's intensity enhancement here, here, here. So this and then the reason I mean Miyoshi put them together, try to demonstrate the behavior of those lower 10 keV electrons show similar pattern as those at very high energy ranges. So the takeaway message from his paper, from their paper, is they suggest the relativity electron microburst actually is high energy tail of pulsating aurora energy, pulsating aurora. So next one. And the other interesting measurement is by comparing the SEMPAX relativity electron measurement with the ground-based all-sky imager GRIL. So here's also the 45-second snapshots of the aurora image, the patchy aurora image. And then on top of that, you have the SEMPAX trajectory mapped to the image. So and then on the bottom shows comparison of the SEMPAX relativity electron measurement against the intensity of the all-sky image along the trajectory of the SEMPAX. So here, so the black line is the electron measurement from the SEMPAX, and then the the green bar represents the intensity of the all-sky imaging along the trajectory. And then this original measurement, original flux, and then you do a detrain, it represents the red line. Now you start to see the correlation between the relativistic electron flux with the enhancement with the enhancement of the aurora intensity, patchy aurora intensity. So this is also supporting the Mioshi's finding that is the electron precipitation due to can cover a range of energy electron energy up over the by 2 orders of the magnitude, at least 2 orders of the magnitude in terms of energy. Okay. And then how to
sorry, Lenjie, may I have a quick question here?
Yeah.
So maybe I'm not getting enough from here. So what's a typical spatial scale size related to this microburst? From the image, it looks like very large. I'm not sure if is this a right interpretation?
Yeah. So actually that I'll talk about the size next slide maybe.
Okay, sure.
So first of all, how to account for electron precipitation over such a wide energy range? So although there are other ideas, but people believe that the coarse wave is the primary driver for electron precipitation over this wide energy range. So the coarse wave, as I mentioned, also shares a similar features like a short duration and then very impulsive nature. And then in terms of physics, so basically through the draw resonance with coarse wave, and each resonance at the resonance, when the resonance transition is satisfied, the electrons get kicked in their pitch angle or momentum, and then they change the pitch angle, and then when a group of electrons interact with the coarse wave, they follows the diffusion, pitch angle diffusion process, and then they gradually push the electron into the loss cone where the electron flux is lowest. So dry resonance condition, if you look at the dry resonance condition, it's very simple. Just the Doppler shift wave frequency matches the electron draw frequency. But in the magnetosphere, you have to take into account the bounce motion of the electron, and then the inhomogeneity of magnetic field along a different latitude. So if you write this, if you look at the latitudinal, and also another thing is the course is short-lived, so you have to take into account the time dependence of the frequency and latitudinal dependence of the frequency, and that is actually the time dependent and the latitudinal dependent draw resonance condition. And then the ideas. So if the coarse wave are believed to excite at the equator, and then when they excite the equator, they resonate electrons at relatively low energy, like a few keV to 10 keV range, and then they scatter the electron, and then to the loss cone and leading to the precipitation. And then the coarse wave will propagate along the field line, and as they propagate along the field line, they interact. The resonance and the increase in magnetic field will lead to the increase of the resonance energy. So when the coarse wave move away from the equator, they start to interact with the higher and higher energy electron. And then if the coarse wave are able to propagate to sufficient high latitude, they can interact with the relativistic electrons, and therefore you can see a wide range of electron precipitation through the coarse wave propagation along the field line. And then because of the coarse wave, it takes like less than a second also to coarse wave to propagate from the equator to high latitude. So if you look at the electron observation at the NEO satellite here, you tend to see alignment of the more or less alignments of the electron precipitation at the low energy and electron precipitation at the relativistic energy range. And therefore, and then also the coarse wave come with groups. So if you have three group here, a three coarse element as a group, one group, and then another three coarse element as another group, then when you do the, you can expect you're going to have 3 internal modulation of the low energy electron precipitation, and separated by a certain period when there's no coarse wave. So you start to see those smaller fine structure modulation and then larger scale pulsation, like turning on, turning off thing. Yeah. So that is the overall summary of the physical process responsible for the electron precipitation over a wide energy range. And then the
hi Lonnie, sorry. I have a question here. I'm curious about the time delay from the generation in the equatorial plane when it's reaching the ionosphere. So from this diagram, maybe not drawn to scale, but I suppose one packet is just a few seconds, but that delay seems to be a fraction of that.
Yeah, the propagation time delays and the propagation time scale from the equator to high latitude is less than I think it's like a 0.1 second or so, because the coarse wave travel like 1/10 of speed of light. So
1/10 speed of light. Okay, thank you.
Yeah, it's about the velocity of electron at maybe 10 kV or 200 kV range. Yeah.
I see. Thank you.
Yeah. But of course, if you want to model the electron microburst due to the coarse wave, you need to take into account those time delay. Yeah. Okay, so I think there's some more evidence to support this idea of that coarse wave is primary driver for the electron microburst. So if you look at the statistics, so between the coarse wave intensity and then the electron precipitation flux, this from the poles, this from the crest for the equatorial, for the coarse wave intensity. So you can see they both electron post electron flux and then the coarse wave intensity increases with the increasing AE indexes as expected. And then the non-linear, if you look at the spatial distribution, they tend to cover similar spatial regions. So pre-midnight all the way to the known sector, and that is consistent with the electron transport path from the injection on the night side and then drift toward the dawn and then the noon along the magnetic gradient drift, and then before they decay away, and then you see a minimum at the dark sector. So that supports again the electron precipitation and then the coarse wave are well correlated. And also there are some fortunate conjugate observations, and this is the SEMPAX observation. So you can see this is an individual microburst, and then at about the same time, but the wind measures the burst of the Wisdom wave at about the same time, although this nuclear time is slightly off. But you can see the temporal similarity in the bursty nature also support the coarse wave drives the electron microburst. And the other, back to your earlier question about the size. So fortunately, we have a way to estimate the size of electron microburst. So, but you need to use multiple satellites. So here's the example of the 2 AC6 CubeSats measurement. So I use this example. So there are 2 measurements. One from this 2 CubeSats, and then blue and red, and then the satellites are separated about 5 kilometers. So you can see the temporal profile looks very similar. They see the enhanced and then the maximum minimum about the same time. So meaning the 2 satellites observe the same microburst structure. Okay. And then if you shift to the
Lunjin, I see Mary raising her hand.
Yeah, I just had a question about the Kirsten study. I mean, wind is out in the solar wind at L1, right? So what is the implication of seeing? I'm missing the point of what the implication of that wave packet seen at wind is relative to sample.
Oh no, this is like wind actually has I don't know but the wind has a time in the L near the 4 to 6.
it had a time period when it was at 5 to 6. Oh, wow. Huh.
Yeah, I think that according to their paper, they mentioned there's a
in 2000. Okay, all right. Okay, thank you.
Yeah. For back on this one, so but if you do the offset by the orbit separation, you don't like you offset the time by 1 second, so they basically measure the same measure the flux at the same location. You don't see any correlation, meaning this observing the structure of this is more like a temporal structure, not the spatial structure. And then if the two satellites separated by the 60 kilometer, you also see similar structure. This different event, meaning this structure, this microburst size can be up to the 70 kilometer, at least for this case. And then in this Shinko's 2020 paper, they map the size to the equatorial region, and you can average microburst size when you map to the equator is about 20 kilometer. And then similar thing can be done for the coarse waves. You can have random pole observation, and you can look at the correlation between the coarse wave at the two satellites that is separated in space, and you can get a similar estimate of the coarse wave size, transverse size, which is about 300 kilometers. So I think they are quite comparable. So which also support the relation between the coarse wave and electron microburst. Okay.
I have a question. Sorry, I have a question on the bottom right. What does that DT means? Is that the time span of the x-axis there?
Oh, so this is the actual measurement, but they're separated. The two satellites are separated in position.
Yeah.
5 kilometer and 76 kilometer. On the bottom side, what they do is try to shift the measurement, because the two satellite orbit is very about the same, except that certain time delay. So you shift the one measurement by the time delay, so that essentially they measure the flux about the same location, but not at the same time.
I see what you mean. Yes.
Yeah. So I mean, by that you see that this is not a spatial structure, because if it is spatial structure, you should see the same thing from the bottom panel.
I see.
Okay.
Yeah. Thank you.
Okay. Now back to the. Let me see what time is it? Okay. Oh. Okay. Time flies. So yes, the coarse wave mechanism is very is well, and the observation connection between the microburst and the coarse wave are well established, but the detail of the physics behind how the microburst was formed is not well known. So and then I will show you a reason why later. And then that's why our goal will spend a lot of time to develop model for this microscopic physics process, and try to reveal the formation of the electron microburst driven by the coarse wave. So first of all, one challenging for modeling electron microburst is that electron microburst is a phenomenon that occur rapidly and due to intense coherent coarse wave, so that the traditional quasi-linear diffusion theory does not work. The quasi-linear theory apply in general for the weak turbulence. It's not for the coherent and strong coarse wave. So we need to come up with different method to treat this modeling problem. And of course, we know the coarse wave is important because they drive the electron precipitation, and this electron precipitation is a major source for the diffusion aura, and diffusion aura is important for the ionosphere conductance changes, and therefore, the coupling between the magnetosphere and ionosphere. So I mean the other, as I mentioned, the quasi-linear does not work, and then the way we treat this problem is through test particle simulation. And then the good things about test particle simulation is you keep all those nonlinear physics. So here's the equation we're going to solve. So there's a single field line, and then solve for the perpendicular momentum changes due to the background magnetic field, and then the wave fields, and then also the last thing is also keep track of the electron straw phases, and then because of the phases of the wave determine on the location, therefore the entire equation could be nonlinear. So here, so if you have a field of test particle, you can once you construct the waves, you can throw the particle in, and then you can look at the behavior of pitch angle, for instance. So here's the example of the one. So if this is the equatorial mapped pitch angle, and this latitude. So if you don't have any resonance or everything, the equatorial pitch angle is conserved as you move along the field line. And then once you hit the resonance point, and then the pitch angle start to scatter. And then for the weak turbulence, you start to see the symmetric scatter of the pitch angle. But for the nonlinear high intense coarse wave, you start to see the asymmetry between the asymmetry in the pitch angle scattering. And actually, if you see this one, those electrons can have a electron pitch angle change by 20 degrees. Actually, those are electrons that lock in resonance with the coarse wave. So we call those phase trap electrons. So when you solve those nonlinear equations, you start to see these nonlinear features. But in order to solve this equation, you need to find a way to construct the coarse wave field, coherent coarse wave field. In that, by that I mean you need to construct the coarse wave amplitude as function of latitude and time, and wave phase as function of latitude and time. And that actually require the physics of wave propagation. You need to know how wave propagate, and then how the wave phase changes as wave propagate to the higher latitude. And then the other difficulty for modeling the electron microburst because is that there are several propagation modes. So simply put, there exist two propagation modes. One is ductive propagation mode, the other is non-ductive propagation mode. So ductive propagation mode, now I can explain the non-ductive propagation mode first, maybe. So non-ductive propagation mode is so you have a smooth medium, and the density is smooth, and magnetic field variation is smooth. And then you just need to solve the ratios equation using the Snell's law, and then you can figure out how the groove velocity how the wave energy propagate in space by solving the groove velocity, by knowing the groove velocity. And you also can understand how the wave vector evolve as we propagate by using the Snell's law in the continuous medium. And for this medium, of course, frequency doesn't change. You don't have temporal variation of the background medium. And then you can also work out the damping rate for as we propagate, and then you can solve this set of equation. So, and then once you solve the equation, you can get a phase and amplitude out of it. On the other hand, if you have ductive propagation, which occur when you have a density structure along the field line, like here you have an enhanced density structure along this particular field line, and if you have wave the excited inside this field line, then this wave try to propagate along the same field line, and then with quasi-parallel propagation. And then when this occurs, then the equation becomes simplified. You have parallel propagation, and then you can solve the similar phase equation to get a phase distribution function latitude and time. And you also, but for the quasi-parallel propagation, we don't expect any non-null damping because the wave vector is along the field line, so non-null damping is not effective for the parallel propagation case. So you expect the wave amplitude remain large as wave propagate along the field line. But for the non-ductive propagation, you start to see wave become oblique, and then when we become oblique, and then you're gonna have non-null damping associated with silver thermal electrons in the magnetosphere. And then next slide will show you the differences between the ductive and non-ductive propagation. So here's a summary of the dark conductive propagation. So for the dark propagation, we propagate along the film line, okay, with a 0-degree wave number angle, and then along another same film line, and then the wave. So here's the latitude wave number angle, almost 0, and the wave gain or damping is almost 0 because there's no much damping for the dark wave. But for the non-dark wave, the wave number angle, as you go to high latitude, wave number angle become larger and larger. By you reach the 20-degree, wave number angle can be 60-degree. Then there will be very strong non-damping. And if you look at the damping effect, so as we propagate to the 20-degree latitude, wave suffers minus 20 dB damping, which is about 2 order of magnitude in terms of power reduction.
Hey, Lunji, how do you define the wave normal angle here?
Wave normal angle is the wave vector, the angle between the wave vector to the background magnetic field.
Okay.
The waves are generated near the equator with the field line propagation, but as they propagate away from the equator, they can become oblique.
Yeah, sorry, I may be too ignorant about this. So cos wave or Whistler wave is supposed to ideally just propagate along the field lines, right? But
yeah, the goal velocity is more or less like within 20 degrees along the field line. Energies, wave energy is more or less propagate along the field line, but the k vector, the wave vector k, can be oblique.
Okay.
Even they are oblique, the way the goal velocity, the velocity of wave energy propagation can still be along the field line. As you can see here, this is so at this location, the non-active waves about the 60-degree wave number angle, but the energy still propagate more or less along the field line.
Do you need to assume any background plasma density distribution? Does that matter here?
Yeah. You need to set up the median, background median, because of the wave propagation physics is a linear problem. So you need to know the background distribution, like electron density distribution, dipole magnetic field distribution.
Thank you.
Okay. Moving fast. So of course we're not interested in the individual particles. We want to simulate the behavior of electron flux, entire flux electron, all the electron population within this field line. So the way to do that, we just throw in a huge amount of virtual electrons, cover all the wide range of energy, and then the wide range of pitch angle, and then at the different latitude, and then at the different draw phases. And then also set up the ideal loss cone. So whenever particle hit this 100 kilometer altitude, we consider electron is lost. We will move that electron out of the system. And then so the way to the way to run this model is we set up the course wave, and we get the input, specify the course equatorial course property, and then we solve the wave equation, and then we construct the wave field due to this causal element at the equator, and then we launch particle and then trace all the particles' behaviors, and then we can put virtual points, observation point, like at this neo location, to detect the electrons that can be detected by this location. And then at the end we're able to construct the unidirectional differential flux at any location as a function of the pitch angle, energy, and time. So by doing this, we can have straightforward way to compare against any particle detector and a neo satellite. Okay. So let me give you an example of the study to illustrate how we model the electron microbursts. So this is one of Alphen observation. Alphen is like about 500 kilometer altitude near CubeSat. let me see. So we have events on conjunction event between the alpha and then the valence pole A. So this is shows orbital information of the RBSP and alpha. So they're about at the same L shell, but then they're separated by the I think it's 2-hour local time. And then we from the alpha measurement using this perpendicular this precipitation flux, and then this track flux, and this is the visual perpendicular precipitation and track fluxes. And if you look at the flux ratio here, you see the spikes of the precipitation and of this flux ratio, indicating they are faster. There's a very rapid precipitation occur in those two time instants. And if you look at the measurement over this 7 second and 7 second observation here, and then you start to see. I mean, the alpha particle detector can have alpha is spinning. So as they spin, they can look at the different directions. So essentially, every half spin, 0.5 seconds, they can observe a pigeonhole distribution of electron flux at this low altitude neo location. So here's also the looking at the measurement pitch angle, and this measurement solid line measurement pitch angle, and this is the loss cone, and the other side going to be the anti-loss cone. And then if you look at this time interval here, 7 second time interval here, you start to see this is the previous loss cone measurement here in low flux, and then outside loss cone high flux, and then you enter another loss cone. Now this time the flux is much enhanced. So you see the different from all the energy range on the 60 kV to a few hundred kVs within this local. And then next the time when the detector which inside the loss cone, you see the reduction of the significant reduction of the electron fluxes. So the electron flux enhancement only occur during this time period, which is only like a fraction of a second. So we consider this as a microburst signature by this alpha observation. And as I said, loss cone is quickly filled within a fraction of a second. And then if you look at the flux ratio, you start to see for the low energy, a flux ratio decreases with increased energy all the way to the 700 kV. And then the flux ratio can exceed a value of 1, meaning at this instant, for those low energy range, the electron flux inside the loss cone can be greater than flux outside the loss cone. And that is something that cannot be achieved by the quasi-linear theory. So we know for sure you need to take into account the nonlinear process in order to account for this flux ratio being exceeding 1. And then unfortunately we have some coarse element observation from the valence pole observation, and then basically we take the coarse wave property from the magnetosphere observation, and then using the valence pole observe the electron distribution as an initial condition, and we try to simulate the evolution of the electrons due to this coarse element, and then depending on the propagation mode, you can end up with a very different result. So here's the ducted case and the non-ducted case, and so but I put the virtual detector at the location of the alpha satellite, so at a very low altitude, 500 kilometers or so, and this is also the precipitation flux for the ducted case as function of energy and time over 1 second also, and track flux energy and time, and the ratio between them. And the bottom line is also non-ducted case, the same format: precipitation flux, track flux, and flux ratio. So you can do the conversion first. So first of all, I want to point out a few things. One is the both when you have a course in the magnetosphere, and then if you have detected a neo location, you start to see enhancement of both track flux and precipitation flux So if you have detector at the near location, is the enhancement of flux that may be a mixture of the trap and precipitation flux. That makes sense because as you scatter the particle into the low zone in the magnetosphere, you tend to feeding the lower pitch angle, feeding the flux at the lower pitch angle range. And that can be at this altitude can be inside and outside the low scope. Yeah, so, and then the flux ratio. If you look at the flux ratio indeed decreases with increasing energy. And then if you look at the low energy range, the flux ratio can be greater than 1. And the high energies, like MeV range, the flux ratio is typically like less than 0.5. So that's also consistent with the observation trend. And but if you look at the non-ducted case, as I mentioned, if you have non-ducted coarse wave, then coarse wave energy will be damped quickly before the coarse wave reach higher latitude. And we know the higher latitude coarse wave tend to interact with the more energetic electrons. But if you don't have sufficient wave power at a high energy, at a high latitude, the non-ducted coarse will fail to interact with the relativistic electrons. Therefore, for non-ducted case, the electron precipitation is limited only to about 100 keV, and the flux ratio is relatively weak because of the reduction of the wave power due to the obliqueness of the coarse wave during the propagation. Okay, so here's a quick summary about what I just said. So first of all, observationally, there's strong connection between the coarse wave electron microburst. But we know that the coarse wave is primary driver for the electron microburst, but the detail of the coarse on the microburst formation is still not well known. So in this particular case, I present a case that non-ducted propagation will limit the electron precipitation below 100 keV, but if there's a dense density duct structure, you may be able to account for electron microburst over large energy range, and including the relativistic energy range. I want to ask how many minutes I still have.
We already end at 3 because people have other meetings, but I think I'll let your own decision if you want to briefly go over the rest you have, and we can have a few more minutes for discussion.
I can skip one part and talk about. I mean, I have. I think this will take some time. But I can go. I can go to my future work if you are interested in it.
Yeah, sure. I'm certainly interested in that.
Okay. So I will skip the second part. The idea, second part of my basic idea is, okay, for this individual case, I demonstrate the propagation mode matters. Okay, but for this individual case, and then the second question I will ask is, now we have the coarse wave observation, very good coarse wave database from the example data, and then we have all those elements property, and then we also have SEMPAX microburst duration property, and then can we predict quantitatively the distribution of the electron microburst duration for this by doing the statistical study, making the connection between the two phenomena, coarse wave in the magnetosphere and the electron microburst at the equator. Electron microburst at the near location. And I give you the short answer is yes, we can do that. But I don't think I have time to demonstrate that. So just very quick. So in the left hand side is the SEMPAX observation of the electron microburst duration as function of the knockdown and L shell. And on the left hand side, we have the calculated microburst duration based on the coarse wave property. And I think you can see the trend is good. So the lower value at the midnight and higher value on the daytime, which is consistent with the observation with the SEMPAX observation, and also the value actually is quite reasonable. So it's this about the 80 millisecond and this down sector, and we also can get that white. So I think that statistically we do able to reproduce the microburst duration distribution using the equatorial crosswave property. But that's I think I will move forward to the future work. Okay, I think that maybe you are more interested in this. So what I just told you right now is the process occurring in the magnetosphere. So we have electron flux, electron bounce motion in the magnetosphere, and then you add crosswave, and we have a model of the wave particle interaction, and then we add the wave propagation physics. We can simulate the precipitation flux at any location as a function of energy, P-single, and time. And then the next thing we are working on now is try to use this precipitation flux set at the 500 kilometer as output boundary condition for this Gen4 energetic particle precipitation model. Because in my current model, the result I show you, we did not we use the ideal loss cone, meaning we do not treat the collisional process in the current model. We just force the electron to leave the system when they reach the 100 kilometer. But we know that's not that realistic. So if, for instance, if your electron reach the 100 kilometers and going downward, this electron will go through a lot of series of collisional process before the energy is giving away. So for instance, if you have energetic electron, they can they can collide with the neutral particle, deposit energy at the altitude below the 500 kilometer. If this energy, if we have relativistic electron precipitation at this 500 kilometer, then this electron has enough energy to produce the X-ray proton, and X-ray proton can be a source of photonizations and to produce more electron and ion pairs as they going downward. So this part of model that treats collision process through the Monte Carlo simulation is done by this G4 EPP developed by Marshall and Kelly et al. 2020. And then so I can show you and then once you get all those collision process resolved, and then you can get the altitude profile ionization, and then you can throw this ionization profile to the chemistry model to figure out the ionosphere variability, change in the electron density, change in the conductance, things like those can be resolved. And here's just a very simple tryout combining with the G4 EPP model. So these are the example you may saw in my early slides. So it's ideal loss cone, so electron loss at 100 kilometer. No collision process was taken into account. No realistic collision process are taken into account. So you can see that as if you look at the 500 kilometer altitude here, you have loss cone. You don't have in the anti-loss cone is nothing, and those particles in the loss cone will completely remove at later time. And then this shows the electron microburst energy and time profile due to this ideal when you use ideal loss cone. But for the realistic loss cone case, we treat the collisional process, and then you start to see the backscatter electron moving out away from the equator. That what happens is if you precipitate a very energetic electron downward, this electron has enough energy to excite secondary electron almost any direction. Some of the electron will be resisted at this 500 kilometer again as a backscatter electron. And if you look at this on this side, you start to see this contour this struck. We don't see this struck cutoff. You start to see the extension of the electron flux perturbation down to even lower energies. So that's one thing I want to show. And then moving forward, I mean, we'll do some preliminary study to investigate the ionospheric property changes due to this coarse wave. Wave. So here I showed you this before. So what will have impulse coarse element at the equator, and then we do the calculation, work out the flux pitch angle energy at 500 kilometers. So that's some, and in this and for this we take into account the collision process with this still loss cone. So we see the backscatter and then the extension of the electron flux enhancement down to the lower energy. And then on top of that, we also can work out the energy deposition profile through this Dream4 EPP model. And then this is the altitude and time of the ion electron production rate, or Q in the per centimeter cube and then per second. So you can see that this is the log scale. So most energy deposit at about 100 kilometers, and then of course there are over a range of altitude from something like 40 to 300 kilometers. And then with this Q, you can throw into the chemistry model, and this is 5 species chemistry model called GPI5 chemistry model, and developed by this Kepler 2022. And then I can throw in I can use this ion production profile, time dependent, altitude dependent, into the as an input for this GP5 chemistry model, and then I use the initial condition here is from International Reference Ionosphere density model, and then we solve for the 5 species time-dependent chemistry model, and then you can see the evolution of the electron density. And this is the input of the ion production rate due to the coarse element as a function of active and time. And then this is just a cut of the Q at 90 kilometers. So this this Q due to the coarse wave, and this which you see is a pulse enhancement of the Q at this altitude due to the coarse wave. And if you look at the electron density response, you start to see a cumulative increase by at least more than 10% due to this single coarse element. And then once you turn off the Q, because the coarse wave is so lift, then this electron density start to decay slowly back to the equilibrium density. Okay, I think I will stop here and then just share something what I have done and then what I'm going to do in the future. Yeah. Now, if you have any question, I'm happy to answer.
Okay, thank you, Renji. Questions in the room? Online? Oh, Mary, please.
Just down the hall. So I have a question. Did you show observations confirming higher fluxes in the loss cone? I mean, than outside the loss cone? Because that's really counterintuitive to me, since you're always feeding the loss cone with the fluxes outside the loss cone. And
so you're saying this one maybe. So this is the precipitation flux, meaning the flux inside the loss cone.
Yeah.
A flux outside the loss cone.
Okay.
And this is the value is 1 here.
Yeah.
So for those low energies, like below about the 10 kV range, they can the loss cone flux inside the loss cone can be greater than flux outside the loss cone.
And then again, that's probably due to a generation of backscatter filling the loss cone. I would imagine.
No. When we say the precipitation, I mean the flux inside the loss cone, not the in the anti-loss cone.
Yeah. Huh. Yeah.
So,
it's counterintuitive to me because you have to feed the loss cone always with the flux that's outside the loss cone.
Yeah.
Constant.
Then that's and that's why this is that's a typical picture of quadrilinear theory. They try to smooth out the gradient.
Yeah.
But in the for instance, I think here when you have very strong waves,
Uh-huh.
in the process is not like a diffusion process. you can see in this 20-degree, for instance, this 20-degree pitch angle can
Yes,
scatter to very low pitch angle
yes,
with one resonance.
okay.
So that tends that I mean by doing that you start you can have a electron jumping from high pitch angle to low pitch angle without go through the intermediate pitch angle. So it's not like a
Yeah.
And I don't have time to show here, but in my simulation I also see the similar thing. You see the precipitation flux sometimes can be greater than track flux. If you look at the ratio here, the green is about 1.
Yeah. What is that? Was that Elfin measurements you were showing?
And this one is alpha measurement.
Yeah. And what is the field of view of the Elfin detector? Do you know, or I can?
No, field of view is, and so the I think so. So if you look at here, I think I'm not for sure, but I think that it's relatively level, and then that's why they can resolve the pitch angle distribution. Otherwise, it's difficult.
Right, yeah. Because a counterexample is in the POSE data, which of course doesn't have terrific pitch angle resolution. The detector looking perpendicular to the magnetic field, which is always looking at trapped flux, always sees a couple of orders of magnitude higher flux than the detector looking along the field, which is also probably seeing some trapped flux as well as the precipitating flux. It's always a 2 orders of magnitude difference between them. So I'm really surprised at this observation. I've never seen it before, but I haven't looked at the low energies. Yeah. Thank you.
Okay, I have a quick follow-up. I just found that Pi GPI5 model mentioned by Stephen Kepler. So this looks like a open source tool for the studying the impacts of the energetic precipitation in the ionosphere thermosphere, especially at the lower altitude. I guess maybe we should consider implement that in WACOM-X if it's not already available, so that we can better evaluate like some global impacts, or to whatever extent it may have. What do you use? Like you show here is you mentioned it's IRI, just like an empirical model, right?
The initial condition,
initial condition, right? But I guess maybe it's worthy of investigation if we can combine this tool with the WACOM-X global atmosphere model to see more general impact. Okay. I think I have many more questions for you, but I don't want to hold people for too long. A very quick one is, what's the explanation for that intermittent bursts within like one packet in the beginning? The microburst, you see a train of spikes, right, within one packet. So what determines that intermittency?
You mean
maybe on the first slide? Yeah, here you see there's different spikes. So what determines, rather than a continuous one, why it's showing as a few spikes there?
You mean this one or
here? Yeah. Just
this one?
This one, the three.
This one is simply you have 3 causeway elements.
Okay, determine the wave elements.
Yeah, so this is 1 element, 2 element, 3 element. Each element correspond to 1 peak.
Okay.
And then causeway element come as a group. So this one group, second group. So that's why you have one group here and one group here.
So basically, it's a causeway wave themselves are behaving like this bursting mode.
Yeah.
Related question. So I just maybe a kind of general question on the source of the chorus waves. Are chorus waves always at a constant level, or are they episodic or intermittent, up and downs?
Up and down
means going like the wave activity goes up and then maybe gone for a while, or maybe it's pretty much generally stayed at the similar level.
Oh, okay. So it's so you mean the whites and there's a gap and then
maybe a more general question. So what are the sources for chorus wave and for its variability?
Okay, so the chorus wave, so there are two phases process. First phase is linear phase. So linear phase is driven by the linear instability due to the electron temperature anisotropy. or which can be developed by inward transport. And then when the wave, but the linear phase give you a broad frequency range, and as long as you have instability. But the among those unstable frequency, one frequency will that correspond to the maximum growth rate, linear growth rate, will reach the highest power at earliest. And then when this frequency reaches sufficient intensity, they start to develop they start to create the resonant let me talk about this. They start to develop structures in the electron draw phases. Let's put it this way, because in the linear theory, okay, electron draw phases still randomized. I still do not show any symmetry in the draw phases, but in the when the wave becomes sufficiently large during the linear phases, then the course will start to develop the structures in the electron draw phases related to the electron draw phases, and we call in this structure will lead to the nonlinear current, and that nonlinear current, one part responsible for the frequency change, the tripping, the other one provide the free energy to the wave to reach even higher amplitude. That's why at the end of simulation, during the saturation process, the course will always appear as very intense and with frequency sweeping. And then in terms of the on and off feature, course wave element, we do have a theory for that. One theory is like this. So if you do the, I mean, we see that in the peak simulation. If you do the peak simulation, you can simulate the course element by using the unstable electron distribution. But that course element, once you generate the course element, the free energy inside this system is quickly released, and then there's no enough energy to excite additional element, unless you have a process like an injection process to continuously flow in the free and the unstable electron distribution to the system, and so we have another simulation with this injection process taken into account. Then we're able to generate more elements, and then spacing of those elements is basically controlled by how fast you inject, you throw in the unstable electron distribution into the system. Does it make sense?
So the very essential mechanism here sounds like it's some kind of instability developing at the beginning to generate the waves.
Yeah. So it's a naturally excited emission due to the electron temperature anisotropy.
Okay. Thanks.
Yeah.
Okay. Thank you, Lunjin. Thank you, everyone. Any more questions? If not, let's thank the speaker again.
Yeah.
Okay. Yeah. Thanks, everybody.
Okay.
The resonance. How big is the resonance? Kind of. It's a resonance system, right?
Yeah, it's basically caused by, like you mentioned, it's anisotropy in the electron temperature. So like in the magnetosphere, like in the tail, usually with those injections, you can easily result in such a anisotropic distribution, and then for the energy to relax, it will excite like the Whistler mode waves.
I see.
Yeah, so CAR is basically is a kind of Whistler mode wave.
And how often does this happen?